Somewhere in a cupboard right now, there's probably a jar of honey that's been sitting untouched for years, maybe since before you can remember buying it. And if you opened it today, it would almost certainly still look exactly like it did the day you bought it. No mold, no sour smell, no sign that anything has gone wrong at all, which, for basically every other food in your kitchen, would be genuinely strange. That's where the famous claim comes from, the one you've probably heard repeated as fact. Honey never spoils. Archaeologists have even recovered pots of honey from ancient Egyptian tombs, thousands of years old, and found it still technically edible. That story gets repeated constantly, in articles, in trivia nights, in half of the Amazing Facts videos on this platform. So is it true? Is honey actually immune to time itself? Let's take that claim seriously for a second, because it's not just internet folklore. It's close enough to true that it's fooled scientists too, for a long time. The reasoning usually goes like this. Honey is basically pure sugar, and sugar is a preservative. That's why jam lasts longer than fresh fruit, why cured meat lasts longer than raw meat, why syrup doesn't rot on the shelf. Honey, the thinking goes, is just the most extreme version of that same trick. So extreme it becomes permanent. And there's real appeal to that idea. It would mean honey isn't just long-lasting, it's essentially outside the normal rules that every other food obeys. A kind of edible time capsule. Except that's not quite what's happening. Honey is not sterile, and it is not immortal. Under the wrong conditions, it can absolutely spoil. The same jar of eternal honey can ferment, sour, and go bad faster than you'd expect. So if honey isn't magic, what's actually going on in that jar? The answer turns out to be less about honey-defying chemistry and more about honey being unusually good at exploiting it. It starts with where honey comes from. Fresh flower nectar is mostly water, a thin, sugary liquid that would be an easy meal for almost any microbe. Bees don't just store that nectar unchanged. Back at the hive, they pass it between workers, add enzymes, and fan the comb with their wings to evaporate the water out. What's left behind is a dense, concentrated syrup, mostly glucose and fructose, with a fraction of the water it started with. Now, here's the part. Most explanations get slightly wrong. It's not simply that honey has low water content. What actually matters is how much of that water is available for microbes to use. Food scientists call this water activity. Picture a packed dance floor where every single person is already locked into a slow dance with a partner. The room is full of people, but there's no one free to pull in and start something new. That's what's happening inside a jar of honey. The sugar molecules grab onto the water molecules and hold them tightly. The water is technically still there, but it's locked up, unavailable, useless to any microbe trying to survive. Research on honey chemistry puts its water activity around 0.5 to 0.65, far too dry for most bacteria, yeasts, or molds to even get started. For a microbe that lands in full-strength honey, this creates a serious problem. Water actually gets pulled out of its cells, drawn toward all that concentrated sugar, leaving the microbe unable to keep the internal balance it needs to function, let alone multiply. That's the primary defense, but it's not the only one. Honey is also naturally acidic, typically somewhere between pH 3.2 and 4.5, largely thanks to an acid produced during the bee's processing of the nectar. Acidity alone won't preserve a food. Plenty of acidic foods still spoil. But layered on top of that already hostile, water-starved environment, it adds one more obstacle most microbes simply can't clear. And then there's the detail that made honey chemistry famous, an enzyme called glucose oxidase, which bees add during processing. In full-strength honey, this enzyme is mostly inactive. There just isn't enough available water for the reaction to run. But dilute the honey, add water, and that changes. The enzyme reacts with glucose and oxygen to produce gluconic acid and something you'll recognize, hydrogen peroxide. A genuinely antimicrobial compound. Not a constant force field sitting in every spoonful, but a backup system that only switches on once water enters the picture. And that backup system isn't identical from jar to jar. Different flowers give bees different raw material, which changes the acids, enzymes, and plant compounds in the final honey. Manuka honey, for instance, is widely studied for a separate compound called methylglyoxal, giving it antimicrobial properties beyond the peroxide system entirely. Honey isn't one single chemical formula. It's a whole category of slightly different defensive recipes, all built on the same basic strategy. So the entire defense system depends on one condition staying true. Keep the water out. Break that condition, and the rules of the jar change completely. Leave honey somewhere humid, mix it with water, or harvest it before bees have reduced its moisture enough and its water activity starts climbing. The sugar solution becomes far less hostile. Certain yeasts, the kind adapted to tolerate intensely sugary environments, can finally find enough usable water to grow. That process has a name you already know: fermentation. It can produce bubbling, foam, a sour or alcoholic smell, and a completely different flavor than what you started with. In fact, humans figured this out early enough to turn it into a drink. Mead is honey deliberately mixed with water, so yeast can convert its sugar into alcohol. The exact same property that protects sealed, concentrated honey becomes fuel the moment that water barrier comes down. There's a texture change people often mistake for spoilage too: crystallization. Over time, glucose can separate out of liquid honey and form crystals, turning the honey cloudy, grainy, or solid. That's not microbes taking over, it's just physics, and crystallized honey can be perfectly fine to eat. But stable doesn't mean sterile. Honey can carry dormant spores of the bacterium Clostridium botulinum. In intact, low-water honey, those spores simply can't grow. The environment is too hostile even for them. For most healthy children and adults, that's a non-issue. For infants, it's a different story. An infant's digestive system isn't developed enough to control those spores the way an adult's can, which is why health authorities, including the FDA, recommend no honey at all for children under 12 months old. It's a rare exception worth taking seriously, precisely because everything else about honey's safety record is so unusually strong. So, does honey really defeat time? Not exactly. What it defeats is water. Bees take a thin, vulnerable liquid and transform it into something dense, acidic, and almost impossible for microbes to use, as long as that transformation stays intact. Break the seal, add water, and every one of those defenses starts to unravel. The old jars people love to talk about aren't proof that honey ignores the rules of biology. They're proof of how effective those rules become when a food is this good at controlling its own water. Give microbes water, and everything changes. Keep it locked away, and you get a jar that can outlast the shelf it's sitting on. This is reasonable wonder. Big questions. Clear science.